So one thing I will note is that I did borrow most of this from this repo right here. I did modify it slightly for like what we would want to do, but if you want to check out the original repo, I think it's through Udacity's here, but it's public for everyone to go check out. So just know that most of it's in there. Most of these parts I'm importing are just basically for us to make a nice way to plot and stuff like this. Again, shout out to the person who like created this repo because it's actually, it looks nicer than like the plotting will look a lot nicer than my default. So I appreciate them doing this. But first thing we're going to show is like a little bit of an example of like just basic data set, some blobs, right? So you can see here I'm basically creating 3 different blobs with 100 samples total, and I'm just creating a little standard deviation. So like how much those blobs actually like adjust. And I'm creating a random state so I know consistently what kind of thing it'll look like. This right here is basically just to plot it out. This is actually taken from a lot from this part right here. I like the way they plot it. It worked really well. Note that this is kind of like a basic thing. Like, if you wanted to create this like function for yourself for like your work, you might want to put something where you have default parameters, but like you can adjust those as needed. So you can see here, that way you can kind of like plot the same data over and over with certain colors and attributes versus like, literally copying and pasting this whole code over. You can essentially just use this function over and over as you need it. Okay, so just know that's my little helper function there. And so let's go ahead and plot out this data point. So we go ahead and plot this out. You can see here is that we have our little data points, and you can see here's like, oh yeah, that seems like, like 3 different groups, right? You can see it's a little bit, it's got a little noise to it, right? Because I have a little standard deviation. If I increase the standard deviation, we'd have a lot more noise and stuff like that, or the points would be more spread out. Okay, so let's check this out with DBSCAN. So let's try this first attempt. So let's try just like, we're just picking some random, let's say epsilon and some, we'll start with epsilon, but basically the hyperparameters, right? So we'll start with 0.02 or 0.2. And 0.2 will basically be that, what's it called? A little bit of like, like kind of what's in its neighborhood, this kind of like circle radius of like what's nearby. And note that the default is 5. So it's still looking for 5 minimum, or a minimum number of 5 points within an epsilon to call it a core point. Okay, so I'm going to go and call this over. And now we basically do the prediction. So pretty simple, right? But we want to see how well it performs. And that's really what we're trying here. So again, here's another function basically for us to plot out some extra stuff. So this is really cool from the repo. They not only plot out the data like this, they actually have created a function where they also plot out what the epsilon is for each point. So that way we can visualize what DBSCAN will look like. And it'll also plot out what it predicted from DBSCAN. Okay, so we'll see what this looks like. And you can see this is the original data set right here. So imagine 3 kind of clusters, but using epsilon 0.2 and then the number of samples of 5. You can see here, we end up getting 1, 2, 3, 4 different clusters. And then the rest are noise. So you can kind of see a little bit like what's going on. And it's like, okay, like, like we see like this would be the results, and then you just plotted like normal. Like, okay, like, what happened? But since we're kind of going a little bit deeper into this, we're gonna check out, yeah. Sorry,
good question. You said that it also plotted the predictors. Where do you see that in the chart?
The predictors or
the
epsilon?
Didn't you say like it's not only plotting the data, it's also plotting the predicting ones?
I think maybe saying like the neighborhood, because this orange, this kind of purple, this magenta, this purple and green, those is what it's predicted to be each different clusters.
Oh, so it's just plotting what it's predicting then, not
right,
like
yeah.
the training. Okay.
Yeah. And then I think what I did say though, it does plot out this neighborhood, kind of like this epsilon, which we'll see in a second. So note that by default I have it false, so that basically it's not super cluttered. But what we'll see next is we plot this guy, and you can see now that's kind of like the circles around there. So this is really useful to kind of see how it predicted over. Okay. And if I actually pass in, I think that's what you were probably asking, right, Lauren?
I think so. If you go, I think it's plot. Yeah, I think I just got confused because I was thinking it was plotting like like the data that we were training on, not the data that we were predicting on. But now I get that it's training.
Oh, okay. Yeah. Yeah, it's just the same data in this case.
Got it.
Okay, cool. All right. Yeah. So you can see here, this is what we made the predictions, and we can see here in this case, and we can guess what the true labels are. I won't show you guys that, but this clustering labels, you can kind of see that where this epsilon comes through, and you can see basically like a lot of these points just don't have a lot of overlap. So this is a kind of great way to kind of visualizing, oh, how well, our epsilon does. So in this case, we can probably see epsilon 0.2 is just too small, right? we really want some of these points. And for example, these points right here, we really want to connect these kind of together. It doesn't make sense to have really two groups. So we might actually say, okay, let's go ahead and try to increase epsilon in this case. So we'll actually use 0.05, which ends up being the default for DBSCAN. So we'll go ahead and do this, and we'll go ahead and plot out the epsilon, plot out, whatever it labels, as well as the neighborhood with that certain epsilon. Okay. So you can see now that looks a lot more reasonable, right? And you can see here by increasing the epsilon here, we have a lot more points being covered through. There's still a couple right here that are maybe, you could define as, being noise. You can also maybe argue, say, it really should be in this case, or should be included and stuff like that. So one way you can kind of include these extra ones, or maybe doing something where either increasing epsilon or decreasing the minimum number of samples. In this case, I think it would probably be best to increase epsilon just a little bit more, and that might be helpful. You might also want to adjust like the number of samples because it's looking for 5. But yeah, okay. Does this make sense to everyone? Any questions on like how this works and how these relate to adjusting? Okay.
Can we like just for fun change the number of samples to 2?
Sure. Yeah. So what do you want to change?
Well, can we just change that one and just add in another parameter that says number of samples equals 2, or
min samples.
Min samples.
Yeah, let's try that. So we'll have the same thing, same epsilon, but min samples of 2. And you can see here, cool. So it looks like the same, except this case, because there's 2 samples here, and they didn't connect to this part. Basically, this ended up being its own group.
Okay.
So you can debate maybe that's true, maybe not, right? And you can see kind of similar. It's like, oh, if we increase, like, let's say we increase like, let's say 1, right? In this case, we actually get a lot more. Our points are kind of connected together.
Cool. So the min samples isn't actually the minimum number of samples of the whole entire it's just like the minimum within each kind of cluster.
Yeah, it's kind of like saying, what is the minimum number of samples within its epsilon to make it count as a group? So basically you can think of this like saying, like, is it error or is it a group? And so this would normally be classified as error, but since we increased the minimum samples to 2, what happened here is saying, okay, like, well, this is now its own group since there's basically 2 of them right here, but they don't connect with any of these extra border points. But that's why when I increase like to like a slightly higher epsilon, you can see basically it's still minimum sample of 2, but it's crossing over with this original cluster.
Okay, thank you.
No problem. Yeah, and this is where it's really great to just, I think this is a great, if you take like this repo or like this notebook and kind of play around with it, you can kind of get a feel for like, what things change. So this kind of leads us into our next example, right? So this one is a little bit, what's called a varied density. So you can see here is that we have some very dense clusters right here, and then it gets kind of like, a little less dense in here. So we already talked about it a little bit with DBSCAN. Like it might have a trouble with trying to make these groups. So the first thing to do is like, well, let's just try it out. Like, you might kind of have an idea, and I want to keep that in your head like a little bit, like, what the group should be. But let's just try the default 0.05 for epsilon and 5 min samples, right? So if we go ahead and do this and we go ahead and plot it out, let's see what it comes out. And you can see, okay, it looks like I identified this group and this group pretty well, which is probably arguably, like I would say, seems reasonable. And then it looks like the rest of this is noise, which might make sense, but also kind of found these like little smaller groups. And so I want to ask you guys, does this clustering make sense? And then if not, maybe it does make sense, but maybe you would do it differently. How would you cluster it? Like, what would you say the different groups are?
I would kind of put that middle group as one group, like that, yeah, that big circle in the middle.
Mm-hmm. Yeah.
The third.
Okay, cool. I see a nod from Jenny. So like, yeah, I think a lot of people, you could say like, yeah, this should maybe be its own group, right? And then you still have this group over here, group over here. You could also like think of it as saying, well, this should be like one group and one group, and the rest of these should be completely noise. I think that's an arguable thing that you can say. Like maybe this is just kind of like just randomness. It's not really, part of a group. I think you could maybe argue that these actually should be treated as their own group. in certain situations, but it all depends on like what you're trying to look for and like if this makes sense. So maybe, for example, these are clusters, but like maybe these are smaller clusters that started to form and the rest is really just random noise. But I would probably argue closer to like what Lauren is saying, is that I would probably say this might be considered its own group by itself, but it all depends on the context and what situation you're thinking about it as. Okay.
So this is an area where domain expertise could help you make a choice. Like if we're trying to make t-shirts in various sizes and these are people's measurements, we could be like, oh, the ballerinas are this cluster down here and the football players are up there. And then these people in the middle have a bigger spread. So like we could use knowledge to know that like, yeah, there could be denser clusters and less dense clusters in our particular context. Okay.
Yeah, I think that makes sense a lot. So you can imagine like in your scenario, like imagine this is some kind of scale of like height versus weight or something like that. And you might have some people, and generally as they get, let's say taller, they tend to get, like heavier and stuff like that. So you kind of have this like spectrum right here, and you might have like a cluster that forms on this end of the spectrum and this end of the spectrum, but everyone else is more like random noise. So this again might say, okay, like, well, we really care about these two clusters. We want to, let's say marketing or something. Or we really want to cluster this part and this part. Or the rest of this, maybe there's some other thing we can think about, maybe another feature that would separate this cluster out. And maybe think of this as noise, maybe think about this as like everyone else kind of like group. It just all depends on your, what's going on. Yeah, good. And that's a good way to think about it, like, right? It's like saying it all depends on like the situation. Okay, so let's kind of play around with this. Let's say we do have something like where we do consider 3 different groups, like Lauren was saying, group 1, group 2, and group 3. So basically the bottom left, the middle, and the kind of like top right-ish. Okay, what kind of parameters would we give? So we have our defaults, which I have, there's 0.05 and 5. That's what we have up here. Okay, how would you guys adjust this? How should we adjust epsilon or min samples?
I would lower min samples.
Okay, lower min samples. So like 2?
Yeah, 2.
Okay. And then Lauren?
And increase the epsilon.
Okay, increase epsilon. Okay, it's like what value you're thinking?
I would do 1.0.
1.0?
Yeah, that might be too big.
Okay, we try it out, right? So you can try this out and let's see if we do any better. So we're looking for 3 groups, right? And hey, that's not bad, right? So we're pretty good here on the first try with epsilon increasing larger, right? Also min samples of 2. Note that we still get a little bit of, this extra part right here might not be exactly right. So we can kind of keep, modifying and stuff like this. I'll show you an example of that, like a possible solution. So this isn't the only solution, right? It just depends how you do it. I did epsilon of 1.2, so I did increase epsilon. I also increased the minimum number of samples to 10. And that's basically to avoid this kind of thing over here. So if I do this part, you would see is that we still have like this cluster, but we still have a little bit of noise and stuff like this. So it all depends if you want to capture all of that as like one group. If you wanted to capture this kind of like all of these as one group, this might be a closer, what's it called? A closer like what you want versus something's like, oh, you're okay with more noise and stuff like that. We can have this right here. Okay, cool. Note if we increase epsilon too large, what will happen if you increase like, let's say 3, something really large? What would end up looking in this graph? I see Lauren going like this.
It would like, the whole thing would be 1, I would think.
Yeah, and basically that's true, right? It's so large, basically, it's going to include everything. So it's going to become one big cluster, which probably isn't super helpful in this case. Okay, cool. All right, so let's try another scenario. So same data set, but this time we want to have it where there's 2 clusters, one right here, and the rest in the middle are like noise. So starting with our defaults, right? So remember our defaults ended up being about, this cluster and this cluster. How would we adjust this? So I'll put this, the default here just so we can kind of see it.
I think you could either maybe increase the min samples.
Okay, so let's say increase.
Decrease the epsilon.
Okay.
No,
so
increase the min samples. I would do that.
Okay. So what kind of number would you want for min samples?
Maybe 10.
Okay, try 10. Okay, so let's try that. So keep epsilon the same. We'll increase the number of samples. And hey, Okay, that looks pretty decent, except now we got another group right here. Our group definitely got a lot smaller because this has a different density than this density over here, right? So maybe not quite, right? So like, but like, it looks like we're closer to like what we'd want. How can we kind of go from here to maybe get this just green, or maybe even increase this into a bigger group?
We just went from 5 to 10 on min samples, right?
Mm-hmm.
Can we do something in between? Can you do half?
Sure.
No, you can't do half. It has to be full.
It's 6.
It has to be. Okay.
Yeah, we can't do 6.5 sample.
Okay.
Yeah, imagine these are like single points, right? So can't do too much. But let's try something like 6, right? Because we'll do more 7. 7's more middle of 5 and 10. So, all right. So we got this bigger, but you can see there's still definitely like this little groups that are forming here. So, like maybe there's something else we can do. What else could we try doing? Because we're close, it looks like, right?
The epsilon to
decrease epsilon.
Yeah. Wait. No, decrease the epsilon. Yeah, to maybe 0.4.
Okay. I'm gonna go a little bit further. I'm gonna go 0.3, just to kind of.
Okay.
Why not, right? And you can see a little too small, right? So the problem is here is now that epsilon is much smaller, so it's looking for a denser thing. And I'll use 0.04 since Lauren asked it. And we basically made the groups smaller in this case. They have to be more closely tight together. We actually, in this case, want to make it so we're obviously detecting this very dense area, but we want kind of like this. If I were to like rank the different groupings, this would be very dense. This would be not so dense, and this would be like really sparse, right? And so I actually want to adjust it so I consider more dense parts. So I might actually do the opposite where I increase epsilon. So let's try like something like 0.9. And let's see there. In this case, you're like, oh, cool. Like I did get those 2 groups, but now I have too many here. So in this case, I might do something like, well, okay, like this is too dense. I might decrease epsilon, but I might also just increase the number of samples. So let's start something like 15. And so like, okay, let me try that. And you can see, hey, okay, not bad. And this is where like you can kind of like, obviously adjust and stuff like this. When I tried earlier, I don't remember what the numbers were, 1.5 and 40. So I know that's very different from what I have here, 0.9 and 15. So let's see what 1.5 and 40 looks like. And you can actually see it does a pretty similar job. In this case, I actually get a little bit more points on here, maybe like 1 extra point with this purple down here. But you can see it just all depends. And you can see these clusters or these hyperparameters are very different from each other. So you can imagine like going through this, like you can obviously see this kind of a pain, right? Like you can imagine like adjusting it over and over and trying to get that right spot. So one thing we can do, which will actually lead really well into pipelines, is something called a grid search. And basically the idea of a grid search is that we can search for many, many different values of hyperparameters. So you can imagine like this grid of like, saying, okay, different epsilons and different min samples and like test each one of those combinations. So again, I'm just going to use this thing to help us plot out the information. So this will actually create a grid, which is pretty cool. I'll use that same data that we had before. And then in this case, I'm going to go and create a grid of essentially try out epsilon of 0.03, 0.05, 1, 1.3, and 1.5. And then min samples of 2, 5, 10, 20, 80. So you can basically see here, these are going to create different combinations, basically 0.3 and 2, 0.3 and 5, 0.3 and 10, so on. So this will create 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So 5 times 5 will be 25 different possibilities. So note that when I run this is going to take a second, right? Because it's basically got to train each one of those 25 parts. And if you look back on here, this took about half a second, 631 milliseconds. So this total one, 25, it should be about 12 seconds, which you see about 11.6 seconds. So you can see it basically had to train each individual one. And you can see in this case, make sure this little grid, again, the person who created this repo is great. Make this like little helper function. I did not create this, let me get it really clear. But you can see here, we start off at the top left here, which basically 0.3 epsilon, and then we go off to the right, 0.5, 1, 1.3, 1.5. So we're increasing that epsilon. And then our min samples, we start with 2, and then we increase the min number of samples. So you can already see is that if we start off with like very small values for both hyperparameters, we get a lot of different little groups. And then as we increase, epsilon, basically, we're saying it needs to be more dense before we consider it a group. So you can see here, this needs to be really dense and everything. But then eventually, we actually end up swallowing the whole thing. And you can see here, if I start like, let's say midway on the epsilon, if I start increasing the number of minimum samples, it needs to be dense enough so it won't start considering this middle part, essentially, until we get down to the very near bottom here, where basically only the most dense parts are actually considered. Okay. So you can see here, this is actually a really great way to kind of demonstrate what grid search looks like, essentially. We're testing out all these different hyperparameters and seeing, you know, how it performs. And obviously, each one of these are right in their own context. It just depends exactly what are you looking for in this data set. Okay. Does this make sense? Cool. Any questions about how this was produced?
I have a question.
Yeah.
Okay, so obviously in 2D, it's pretty, you can just kind of look at it and be like, okay, we wanted one with like 2 groups. But let's say you have like several features, then what would you be looking for?
Mm-hmm.
I mean, would you just look for like, I guess just like train and test, or is there like a specific metric that a lot of people use for DBSCAN to kind of know if it's good or not?
Yeah. So this is a really tough one, right? Because one thing I'll say is that you could try to use numbers, but sometimes that's really hard to like really get a hold of exactly like what this value is. The main metric we're using is basically distance, right? Saying like how densely packed are they together. Really, a really great way to like analyze this stuff is visually. But then here comes the problem with 2D, right? Like 2D, obviously, how do you like analyze past 2D, right? 3D manageable maybe, but 4 or 5, you know, multiple features, that can be really tough. This is where dimensionality reduction can really help. For example, maybe only plotting out the most important components like PCA. You can say, okay, let me plot out the most components with the most amount of variance and plot that in 2D and see how well it performs. So you train the whole thing and like all the features you want, but only plot out 2D and see if that seems reasonable by itself. Another strategy, which we didn't talk about, which we'll talk about in the future, called I never know if it's pronounced Tisney. I just think in my head TSNEA. But Tisney here. This is a really interesting strategy of what's it called? Dimensionality reduction, where essentially you can take very high dimensional data sets and project it down into 2D. And those, the main thing, remember, for DBSCAN, we're looking for is the distance of like, you know, like how densely packed, how close are they? Well, Tisney, I don't know how to pronounce it. But this will actually keep the relative distances in higher dimensions, and it'll keep it relatively consistent in 2D, which is actually a really, really nice thing. So you can see here, in this case, this was a clustering of handwritten, what's it called? Numbers. So you can see basically these different colors. This is all the zeros, this is all the threes, these are all the fives, these are all the ones. So you can kind of see it more or less kind of keeps them in like that relative space. What are these, you know, features? They're not really features in this sense because they're higher dimensional. You can imagine basically each pixel being its own feature. So if you have like, let's say a 32 by 32 image, that's like 332 times 32. So like over 900 different features. So it's actually projecting something that's 900 dimensional down all the way into 2D. And it keeps actually the relative position close. So that's kind of like more or less how you would kind of like analyze this and see how it performs. There's also like 3D. I've seen 3D like graphs of this. You might even see this like visualizations of like different clusterings in 3D. But usually 2D is pretty decent enough. I don't know, 3D starts bending my mind and everything like that. Did I kind of answer your question, Andy?
Yeah. I mean, I figured there was a way that people were using it. I was just curious.
Yeah, this tends to be, like I say, it's like the human visual, you know, cortex. Like really is like a really powerful tool. Like it sounds really silly to say it like that because it's not very analytical, but it's really true. Like being able to visualize this information can be super useful. Okay. Oh, you can see here, here's 3D. So you can see like how ridiculous this looks. Good luck, right? And it looks like these are different words and stuff like this. So we'll talk about this in like word embeddings in the future. Okay, so anyway, cool. So that is DBSCAN. I know it's not technically part of the curriculum, but I think it was an important thing to kind of check out and see like how you would kind of plot this in. And it leads us right into grid search and pipelines. So we'll go into that next. Sound good? Cool.